So every once in a while in life, I get overcome with this overwhelming sense of existential dread over a question that I have not yet answered. And I'm so consumed with this question that sometimes I can't even fall asleep until I have it answered. And the most recent edition of this phenomena is the question: is math discovered or invented? And so, lucky for me, one of my close friends is a PhD in math. And so I hit him up, ring, ring, hello. And I say, hey, buddy, I have a question for you. Is math essentially just descriptive of nature? He said, well, what do you mean? I said, well, take a look at me. You know, you can use natural language to kind of explain who and what I am. This is a man. This is a man wearing a gray shirt. This is a man that is bald. And you could say this is a man who is 5'9". You know, you can use math, you could use numbers to kind of describe some natural phenomena. Me, 5'9", right? Or 200 pounds, or whatever you want to say. And he's like, And then I'm like, hold on, consider this, right? Let's take a very simple mathematical concept from basic arithmetic. 1 + 1 = 2. He says, okay, go on. I say, okay, so this marker here, this exists. Can we agree? He says, okay, yeah, sure. I'm like, okay, this isn't a 1. This is a marker, 1 marker. Here is another 1 marker, but it's not a 1. This isn't a 1 and this isn't a 1. And together they don't make a 2, they make 2 markers. And so 1 is just a way to describe a property, right, of this marker. We're saying this is 1 marker. He says, hold on, wait a minute, there's something wrong with the way you're thinking about this. And I said, well, what do you mean? And he says, okay, well, think about this. And then he spent the next 20 minutes, the next 30 minutes, proving to me mathematically that some infinities are bigger than other infinities. And he's like, where's that in the real world, Einstein? And I said, okay, well, you've got a point there. I don't know where in the real world you can kind of see that some infinities are bigger than some infinities. And throughout history, we've come across concepts, mathematical concepts, that make sense, but we have not been able to demonstrate in the natural world. For example, the idea of infinity itself has existed for hundreds of years, if not thousands of years, really. And we didn't really know where infinity applied in nature until we discovered more recently that the universe seems to be infinitely expanding. This is a pretty accepted hypothesis that we have about the universe. It is infinitely expanding. So we found infinity in nature. Another example is black holes. The density in the center of a black hole is often described as infinite, right? Infinite mass. And so the thing about that is sometimes mathematical ideas, or the ideas that we have about mathematics, are proven wrong by nature. This is something that happens as well, right? So thousands of years ago, over 2,000 years ago, the Greeks wrote this book. It's called the Euclid's Elements. And in Euclid's Elements, they say that if you have a line, right, a straight line, and another straight line, and they're parallel, right? I can't really make them parallel, but let's see, like this, right? They will never touch because they're directly parallel to each other, so they will never cross, right? If they were like this, they would cross. If they were like this, they would cross. But if they were straight like this, right, they wouldn't cross parallel lines. This is postulate 5 in Euclid's Elements. And we thought this was true in nature for a long time. And for all intents and purposes, it's a rather practical idea. But what Einstein discovered in the 20th century is that space-time is actually curved, right? In reality, real life, you know, this is a super conceptual idea and concept that's hard to imagine, but space-time, as it exists and as we understand it, is curved. And so the parallel postulate that we thought applied to nature thousands of years ago turns out not to be naturally true, right? So then that begs the question, well, then why is it so logical? Why does it make sense that two straight lines that are that have a distance apart from each other never cross. And this is because math is true in the same way that saying all bachelors are unmarried is true, or that all dogs are canines is true. It is kind of describing itself, right? And what we might discover one day is that dogs aren't actually canines. They're aliens disguised as canines, and then we'd have been proven wrong. But as we understand the universe, as we understand the world so far, all dogs are canines, right? This makes sense. And math kind of functions in this way. And math is solely reliant on deduction. And what do I mean by that, right? Consider this statement. All men like eating liver. I am a man. Therefore, I like eating liver. Does that statement make sense? It makes perfect sense. Is that statement true? No, it's not. Because one of the presuppositions, one of the premises that all men like liver is not true, right? And in the same way, mathematics depends on these presumptions, on these axioms, on these pre-established notions that you can't really prove, but you kind of just state them as intuitive or self-evident. And then we build whole systems on top of that, right? And this is what Euclid does in Elements. He says, well, consider a line. A line is a dot connected with another dot. He's not proving this. He's just saying it as a matter of fact. And so, while it's true, sometimes our mathematical models don't match what we observe in nature, in reality, in the natural world. And then we'd need to update our mathematical models to describe it. And so, we're back at the initial question. Is math discovered or invented? And to phrase this another way, I would like you to consider natural language, right? Let's say English. Is English discovered or invented, right? Is English, right? Did we discover that I can be described as a man? Or did we invent the idea of manhood under me, right? And math is very good at describing, it's very good at explaining, it's very good at modeling reality, it's very good at even predicting reality compared to all the other methods we have of prediction. And it can make sense a priori. A priori means by definition, right? All men are bachelors. But our ideas about math could be based on false presumptions. Could be like saying that all men like liver, right? This is not an easy answer. And the reason why it's not an easy answer is because everyone has a different epistemology. Epistemology means the way that people decide whether something or not is true, right? So I've kind of approached this topic from the perspective of, well, nature is true. Empirical evidence is an indicator of what's true. How do I know that for a fact? I don't. But I know that in my own personal life, science and the scientific method has been very helpful in describing things in my reality, right? But I'm still deciding, right, fundamentally, to base my idea of what's true on nature, on what's true empirically, outside of myself. The real world, the real universe is really real. And because I assume this, then, that will dictate how I think about this question. And another thing I want to kind of leave off on here is the idea of falsifiability. So some people think that math is the fundamental substrate of reality, that everything at its base level is math. Now, the problem with that idea, it might be true, it might not be true. We don't really know. But the problem with that idea is there's no way to prove it wrong. You can't prove it wrong because you can investigate something, let's say this microphone, and, investigate all its properties and be like, well, I don't really understand how math is the fundamental substrate of this microphone. And then anyone could easily answer, well, it's just because we haven't discovered enough math yet, and this can go on forever. But if I made the claim that math is not the fundamental substrate of reality, In principle, you could prove that. In principle, we could somehow find the fundamental substrate of reality. Atoms, quarks, dark matter. We don't really even know what that is, right? But in principle, you could discover that. And then you could prove that theory wrong. And in general, in science, we like to make sure that all of our hypotheses are something that could be proven wrong. Because if you can't prove it wrong, then you can never really know if it's true. And that's all I had to say for this video. On this channel, we talk about ideas like this, math, psychology, physics, big ideas by great thinkers. And that's it for this one. We'll see you in the next one. Peace.